Hello and welcome to lecture 54. This is week 10. We are starting with design of transonic compressor. In last week we were discussing about many important aspects for transonic compressor and which was making base for our future design for transonic compressor. So what all we were discussing was say need of transonic compressor. So we must realize a future requirement for the axial flow compressor, that's what is per stage pressurized to be very high, and that's what is fulfilling our requirement for the future engines with compactness, with lightweight and fuel efficiency. Even that's what is taking care of wider operating range, and such kind of high pressure ratio, that's what is possible by implementing this kind of say transonic cases. What we realize is say maybe in order to have high pressure rise we need to rotate our rotor at very high speed, or maybe we need to change the diameter and other parameters. That's what all we have explored with. Now when we are having our flow at the entry to be supersonic or maybe slightly on high subsonic side, then we can say we will be having initial flow to be subsonic, and that's what will be followed by say passage shock, and later on that passage shock we can say as a normal shock, and that's what was giving say flow to be subsonic downstream. So the change of flow parameters, flow properties from say supersonic to say subsonic because of presence of normal shock, that's what will be giving us very high pressure rise, and that's what we are taking as a benefit, and that's what people they have explored after 60s. So this is what is of special kind with good aerodynamics understanding, good gas dynamics understanding, with which we realize if we will be able to manage our flow at the entry, that means at the leading edge of our say transonic aerofoil, that's what will be giving us benefit. Initially we feel if we will be having sharp edge, that's what was giving benefit in sense of anchoring our shock. But what is happening say it will be working say worst when it is working under off design condition. We have seen off design condition, it may be say change of speed or maybe change of mass flow rate and all those parameters, it may be possible that flow will go subsonic in that case. So under that circumstances this is what is not working fine, and that's the reason why we are giving some rounding at the leading edge as well as and when required we will be giving say rounding at the trailing edge. Then we were discussing about say different kinds of aerofoils what we will be using for transonic say compressor. For transonic compressor we have realized those aerofoils are thin aerofoils. Basically we are managing our shock within the flow passage, and that's what was giving us benefit in sense of getting higher and higher pressure rise. So we were discussing about double circular arc aerofoil, controlled diffusion aerofoil. We also have discussed about multiple circular arc aerofoil. We have discussed about S type of aerofoil, and later on after understanding that flow structure we try to get say our camber line, that's what is required for generation of these aerofoils. We also have discussed about the distribution of the thickness over this camber line. So we have considered say circular arc thickness distribution, then we have discussed about say standard thickness distribution kind of thing. Then after having all this idea we have made our aerofoils. Now those aerofoils which we will be using for our future design. This is what was giving say brief idea about what all we were discussing in last session. Now I know you are excited for the design of say transonic compressor, because in open literature you will not be finding such kind of discussion in detail, maybe because of some proprietary nature of the things. That is one thing. Secondly, that's what is little challenging and it required lot of understanding in sense of change of flow parameters. So we will try to discuss in decent way. Let's see what all we know. This is what we were discussing in our week 3. Let's introduce the parameter. We were discussing about the hub to tip ratio. We have realized hub to tip ratio of 0.8, and hub to tip ratio of say 0.4. And what we know, like maybe in the later stages of our axial flow compressor, in say multi-stage axial flow compressor, we will be having our say this ratio, hub to tip ratio, in the range of say 0.4. Maybe on the front side we will be having our hub to tip ratio in the range of 0.8. We say when we are discussing about the fans, mainly those fans are transonic fans, for that hub to tip ratio will be in that range, maybe in the range of 0.4. Then later on what we realize, like with increase of our pressure ratio, the properties in sense of density, that's what will be changing on the downstream of our rotor. If you are assuming our axial velocity to be constant, and if that's what is your case, we will be having say shape of our passage, this will be like that. Okay, here in this case you can see my entry area, that's what is larger, my exit area, that's what will be say lower. Okay, and that's what is satisfying our continuity equation. So we were discussing about the flow three-dimensionality, that's what is happening for such kind of configuration. If we consider these are the streamlines we can plot, that's what is making our flow, that's what is flowing through our axial flow compressor. So when we say we are discussing about the transonic compressor, this is what is now coming into the picture. And as we discuss, say for subsonic compressor and transonic compressor, we will be having the strategies for the design, that's what will be somewhat different. Okay, so let's move it. What we know, we have realized, say in order to satisfy our radial equilibrium equation, we have come up with Cw into R equal to constant. And later on what we realize is, say people they have modified the law of changing this say wall velocity component or say load distribution. What they are doing is, say they are assuming Cw into R equal to constant. If we are putting n equal to 1, that's what is saying like free vortex design concept. Generally this n, that's what is varying in the range of -1 to 2. Okay, so if we are considering, say if we assume our m, that is what is in the range of 0.7 to say nearly equal to 1, that's what is giving say relaxed free vortex design, and that's what is giving say overloaded blade design. Now this is what is very important when we are discussing about the design aspects. What all designs we have discussed up till now, that's what is of say subsonic compressor design. Then we have discussed about say contra-rotating configuration, that also we have discussed in sense of subsonic configuration. Now if we will be having n, that's what is greater than 1, we will be having our loading, that's what we say it is underloaded kind of configuration, and we are taking n equal to -1, we say that as a force vortex design. Okay, so it is designer's choice what kind of vortex distribution he or she will be selecting at the entry of the rotor, at the exit of the rotor. Okay, now what all we have learned, it says when we are talking about the most modern design, we are having a lot of flexibility in sense of doing the design, and as we have discussed, what we realize is, say you are applying your law for the design, and based on that whatever blades you will be making for rotor as well as stator, and if it is working fine and it's giving what performance you are expecting, that's what is your design. So under that flexibility, what it says, near tip and hub section mostly we are having say offloaded configuration, where we are assuming our exponent to be 2, and it says with the justification, say that's what is reducing your tip as well as other end wall losses. So in week 3 we were discussing about these aspects, so you know better now, and if not, maybe you can revise that part again in order to have detailed understanding what we are talking about, say end wall losses. Now at the mid station we can understand at the hub and tip we are mildly loading, that's what is say offloaded kind of configuration. That means at the mid station we need to load slightly on a higher side, and it says under that configuration your exponent you need to select as say 0.8. There is nothing wrong if you will be going with say free vortex design concept, but we know the limitations of free vortex design concept, and in order to get rid of those limitations we are moving with some other kind of configuration. Okay. Now this flexibility, that's what is lowering your losses. That means it is improving your efficiency. At the same time, we are also looking for, say, better performance in off design condition, as well as we are looking for, say, wider operating range. So all this configuration, that's what will be coming after the experience, or maybe if we are talking about engine design manufacturing companies, they are having their own database, they are having their own design philosophies. So for all the stages, as we discussed earlier also, all the stages, they are not same, they are different. You need to design each and individual stage indigenously, and that's the reason why we are having whole lot of research and development activities. That's what is going on for the design of axial flow compressor. So when we say we are launching, say company is planning to launch new engine, that means that's what will be giving whole lot of different design aspect, approaches, and we are having detailed understanding. And we will be having, say, inclusion of universities as well as research center as well as company. They all together, they are developing this kind of compressors and fans. Okay. Now when we are discussing about the high bypass ratio fan, it says this design, that's what is with some different design approach. When we say different design approach, what is the reason? It says our inner stream, what we are talking of. Suppose if I consider this is what is our fan. For that fan, my inner stream, that's what is supplying my compressed air to, say, downstream core region, or say maybe downstream, say, compressor. And my upper stream, that's what is bypassing their air to duct. So under that condition, this lower part, that's what has been designed for low loading. Okay. At the same time, my upper part, that's what we can load on higher side, because we will be taking our benefit in sense of having higher diameter. That means we are able to increase our peripheral speed, and that's what is giving the benefit in sense of doing the design. So now here in this case, under special conditions, it says we are violating our radial equilibrium equation. It says work done, that's what is varying with radius, and that's what is non-zero. So that's what is a special kind of design. We will be approaching, or we will be discussing about such kind of design configuration in this week. Okay. Now in order to start with, let's take one of the design for our calculation. So what it says, we are having our startup company, that's what is planning to design the engine for UAV application. Now this is what is a recent trend. People, they are moving towards, say, unmanned aerial vehicles. So let's take one of the design configuration for such application. So designer has selected axial flow compressor stage, that's what is designed based on fundamental design approach. The air enters the rotor at temperature of 298 Kelvin and pressure of 101325 Pascal. So you can say that's what is your atmospheric condition. Now, and that too, it's on ground. Okay. Now my tip radius, that's what is, say, 260 mm, and assume up to tip radius ratio at the entry to be 0.375. So as we have discussed, when we are doing the design for our front stages, that's what is in this range only. Okay. The rotational speed must be kept under 16,100 rpm based on turbine rotational speed, and prefer to have the relative Mach number should not be exceed by 1.4 at the tip. Okay. The stage need to generate the pressure ratio of 1.63. So that's what is slightly on the higher side, with mass flow rate of 38.69 kg per second, and take the value of Cp as 1005 kilojoule per kg Kelvin. Okay. Now here in this case, that's what is given to us, that's what is, say, we are looking for compressor to be designed, that's what is having pressure ratio of 1.63, and our temperature and pressure, that's what is given. our rotational speed, that's what is given as a constraint. It says like we should not increase our rotational speed beyond 16,100. Okay. Now under this condition, we can say we are having constraint with our diameter of the casing. We have like inlet dimension or inlet radius ratio that is also given to us, and it says my tip Mach number should not be exceed by 1.4. So we can say these are our design constraints. Okay. Now in order to start approaching this design, let's see what all we can do here. So based on available data, as we have discussed, we are having constraints with 3. That's what is my casing diameter. We have constraint with our rotational speed. We have constraint with our tip Mach number. So how do we start doing design for such transonic compressor? You can say my Mach number at the tip, it is given 1.4. That means this is what is the indication that this compressor is of transonic nature. Okay. So what we can do, we need to estimate the size and the speed, because we are not aware of what will be the dimensions for my blades, both for rotor as well as for the stator. Okay. Now what all calculation we will be doing for transonic compressor, we know we will be doing our calculation at 75% of our span. Now at 75% of span, we can say that's what is the mid section. Okay. At that mid section, we are looking for different velocity components to be known. Now all those velocity components, that's what will be helping us for calculating different flow angles. Then we will be calculating our parameters like diffusion factor, degree of reaction, de Euler's factor, all those parameters, that's what we need to decide with. Now once we are deciding with these numbers, we are also interested in what will be the number of blades for rotor as well as for the stator. Okay. And we are looking for different angles which we will be using for making of our say compressor, in sense camber angle, stagger angle, deviation angle, all those parameters. So at mid station, we will be doing all our calculation. Now after doing this calculation at the mid station, we will be applying our design law at different locations, at the entry as well as at the exit. Now here in this case, it says like we need to go with the fundamental design approach. So we will be moving with that part only. Now for practice, you can even try with free vortex design, even you can try with the force vortex design, even you can go with constant reaction design. It's you need to decide what approach you will be selecting with. So specifically for this design, we will be moving with the fundamental design approach. Okay. Now as we have discussed, we are more interested in calculating say geometrical dimension, that means what will be the size. Okay. Now based on input parameters what we have, we need to decide with the maximum diameter, maximum speed and mass flow rate, these 3 parameters, that's what is defined to us. Now in order to do the calculation for different velocity components, that's what is of our interest. Maybe we are interested in calculation of axial velocity, we are looking for peripheral velocity, we are looking for say velocity component of relative velocity, we are also interested in say absolute velocity component. So in order to start with this design, we have different approaches which are possible. Now here in this case, let's discuss one by one, that's what, and out of which we will be selecting one of the approach. Okay. So what all are the possibilities with us? It says maybe first you can select the maximum diameter and speed as per the design dimension. So you can say our given diameter, that's what is known to us, and rotational speed is also given to us. So we can say this is what we can use for our initial design calculation. Now this radius ratio at the entry, that's what is given to us. So we can calculate what will be our half diameter. Based on that, we will be calculating our axial velocity. We can use our continuity equation for this calculation. Once this axial velocity we can calculate, our next target, that's what we need to check with inlet relative Mach number. So whether it is meeting with our requirement or not. So this is what is one of the approach. You can go in an iterative way also. Okay, so this is what is one of the approach. Say there is nothing wrong in doing this kind of calculation. Second approach, it says you can assume your axial velocity. This radius ratio and rotational speed also you can assume. Suppose if I say radius ratio at the entry, that's what is given to you, that's what you can use. Suppose say it is not given, you can assume your radius ratio. Rotational speed also you can assume. Suppose if you are doing design for high bypass ratio fan, you can assume this rotational speed to be in the range of 3000 rpm or 3500 rpm for we are discussing about commercial aircraft. Okay, suppose say it's a military aircraft, we know this will be in the range of maybe 7000 to 12000 rpm. So you just select those numbers. Okay, now with this we need to check with the maximum diameter whether it is meeting with our requirement or not. Okay, then after again we will be checking with our relative inlet Mach number. Okay, now there is third approach. What it says, maybe you can assume CA by U value or flow coefficient at the mid station. This is also one of the good approach. Many designers they prefer to go with this kind of configuration. They are assuming CA by U value. Okay, based on that you will be selecting or say maybe assuming say rotational speed. Based on that they will be doing the calculation for tip diameter. They will check with whether it is meeting with the requirement or not. If not, then maybe accordingly this CA by U value or maybe the speed can be changed. You can calculate your axial velocity. Again you need to check with your inlet relative Mach number. So this is what all we can say. Here there is one more possibility. Maybe someone will say we will be assuming the degree of reaction at the mid station. So it is similar to what all we are discussing here. Say you will be assuming your degree of reaction, that's what will be giving you CA by U value at the mid station, and again you will be doing the same kind of configuration. So the design method, what all we are discussing for transonic compressor, where we are not having information that's what is available with us, we need to assume and we need to follow certain rules. Okay, so these are some of the possibilities. Since for this design some of the parameter that's what is been constrained with, so that's what will be making our life easy, and that will be making say design iterations to be less. Okay, so let's move with the approach. Now before going into the detail, we must understand we are discussing the design of say transonic axial flow compressor. Now we have discussed about the subsonic compressor design, in which if you consider my pressure ratio, that's what is say lower. When I say my pressure is expected, that's what is lower, that means my inlet area and outlet area, we can say that's what is safely to be same. And that's the reason why we are having this kind of configuration, where we are doing all our calculation at the mid station, and then after we are doing our calculation at different stations. Now this mid station for subsonic compressor we have discussed in our all the designs, that's what is done at say 50% span. Okay, then after we will be dividing this whole span into equal number of divisions. Maybe you can take 10 station, 20 station, maybe you can take more than 20 also. No one will stop. It's you as a designer, you need to decide with. More will be the station, it will be more easy to make those blades. Okay, and that's what will be giving you the smooth curvature for the blade. If you will be having less number of station, then it will be making some difficulty when you are start making solid model for that blade. And it may be possible that you will not be having great control for loading or expected performance from particular aerofoil at particular span. Okay, so it's preferred you just go with say more number of say stations. Now when we are talking about say transonic, as we have discussed what is happening, this is what is say my inlet area. Now because we are expecting our pressure ratio to be high, we can say my exit area, that's what will be lower. If we are assuming our axial velocity to be constant, in order to satisfy our continuity equation, it will be giving me my exit area, that's what to be different. Now if this is what is your case, what we need to do, we will be having this conditions at the entry as well as at the exit. Now under that condition, if you look at carefully, say here this is what is a constant mean diameter kind of configuration. Okay, so we will be doing our calculation at 75% of my span. So here we will be doing our calculation. So what you need to do, say this is what is say my height of the blade, we need to calculate this location or we need to locate this point. Same way at the exit of the rotor, we need to locate this point. Same way for stator, we need to locate this particular point at say station 2. At the same way at the exit station also we need to locate this point. Now this is what will be giving you one streamline. We know these streamlines, they are the imaginary lines. Okay, these lines are imaginary lines. So that's the reason why if we are considering this, so accordingly we need to divide say this whole span into equal number of stations. Be careful what all I am talking here. Suppose say this is what is my entry, I will divide this whole into equal number of stations. Same way from here to here I will be dividing into equal number of stations. Same way for stator as well as entry as well as for the exit. Then after we will be joining that with the streamlines. Okay, so we will realize here there is a difference in sense of design. Here in this case what all we are discussing, where we say my u1 equal to u2, here in this case that's what is not the case. My entry peripheral speed and my exit peripheral speed both are different. Okay, here in this case I can say my aerofoil to be two-dimensional aerofoil in sense. Okay, so this is what is a flat kind of aerofoil. Here in this case if you look at, my aerofoil will not be like the way in which we are discussing. That's what will be having third dimension. Okay, and that's the reason why the making of this blade, making of these aerofoils for such kind of transonic compressor, that's what is little challenging. Now based on available tools, computational tools what we are discussing, that's what will be helping us in order to have say perfect shape of the aerofoil. So you need to start with some aerofoil and later on based on your flow physics, detailed flow understanding, you will be modifying the shape of your aerofoil. That's what we already have discussed with. Okay, now here in this case what we will be doing, say let's see, we will be having different kind of configuration, that's what is possible. What we say, we know what is our mass flow rate, so that mass flow rate I say that is what is density into area into my axial velocity. Now this I am representing in terms of say my tip diameter or tip radius. This is what is my entry tip radius. So if you look at, it says this is what is a function of mass flow rate, it's a function of my density, it's a function of my axial velocity, and this is what is my radius ratio. So if you recall, this mass flow rate, that's what is known to us. Even this radius ratio, that is also known to us. Now unknown parameter for us, that's what is say my axial velocity, and even I don't know what is my density. Okay, so entry density also, that's what is not known to us. So what we can do, we need to calculate our inlet density, we need to calculate what will be my axial velocity. So what we will be doing, say we will be assuming our axial velocity in order to do calculation for our entry density. So now here in this case, what we are assuming, say let's assume our axial velocity to be say 160 meter per second. Okay. Now if nothing, that's what is given here in sense of how my flow, that's what is entering, we can safely assume our entry, that's what is axial. That means we can say my absolute velocity and axial velocity at the entry, that's what is same, and that's what we have assumed as say 160. So if we will be using our correlation for total temperature, that's what will be giving me what will be my temperature at the entry. So we say this is what is my entry temperature, entry static temperature. Be careful, do not get confused with the total temperature and do not get confused with the static temperature. So we are interested in calculation of our density. That density we are talking about the static density, that means we are looking for static property. Density we are writing, that's what is say P1 upon RT1, that's what is a static property. So we need to have our static pressure, we need to have our static temperature. Okay, so once we are calculating our static temperature based on our isentropic relation, we can calculate what will be our static pressure. So if we are putting T1 and T01, if they are known to us, we can say this is what is coming, say 86.95 kilopascal. Now once this is what is known to us, we can safely take our density as say P1 upon RT1. Be careful, these units, suppose you are taking kilopascal and pascal, so careful in taking this unit, otherwise this density will not come. Okay, so this density, that's what is coming as say 1.0621. So you can say this entry density, that is static density, that's what is known to us. Okay, now what all we know our say radius at the tip, at the entry, that's what is a function of mass flow rate, density and axial velocity. So we can say if we are putting these numbers, what we have calculated in sense of density, that's what is 1.0621. My axial velocity we have assumed, that's what is say 160 meter per second. If we are putting that, it says my radius at the tip, that's what is coming nearly 0.3 meter, and what we are expecting is 0.26 meter. So you can say this is what is not meeting with our requirement. So again what you need to do is, maybe you can go in a reverse way, you assume your axial velocity and do your iteration. Now in order to reduce those iterations, what we have done, we have assumed say tip peripheral speed as say 450 meter per second. So let's assume this say u tip, that's what is say 450 meter per second. Okay, when we are assuming that, we can do our calculation for the peripheral speed, and based on that rotational speed we can calculate, and that's what is coming 14,324. Now when I say if this is what is coming, this is what is say in acceptable range. Now once we have done the calculation for this ratio, once in sense of my axial velocity, my peripheral speed, we will be checking with what is happening with our tip Mach number, because that's what is our main target. It says my tip Mach number should not exceed more than 1.4. So we will be calculating that part. In order to do that calculation, we will be calculating our relative velocity. This relative velocity we can say based on our velocity triangle, that's what is say axial entry, we can straightway write down Ca square plus u tip square. We can calculate our sonic velocity at the entry, that's what is square root of gamma RT1, and if we are calculating, that's what is coming, it is 1.41, and this is what is nearly what we are looking for, but it says it's slightly exceeding the range. Okay, so let's do some more iteration in science in order to achieve what we are looking for. Okay, now here some of the iterations what we have done with different combination of axial velocity and say your peripheral speed. Here again let me tell you, one can go with say flow coefficient assumption. By that way also you can do this calculation. So in order to showcase what all parameter we need to select with, this is the reason why we have selected these numbers. So if you look at, these are the combination. It says we are looking for our speed. That speed, it is coming in the range what we are looking for. It should not be more than 16,100. For all assumption of axial velocity and tip speed, my speed, rotational speed, that's what is coming in the range. But at the same time, like we are constrained with our diameter. So we are looking for diameter in the range of say 520 mm. So that's the reason why we are safely selecting our axial velocity to be 225 meter per second. Let's assume peripheral speed to be 400. That's what is giving my tip diameter of 0.516. And at the same time, this is what is giving us our tip Mach number to be in the range of say less than 1.4. So it is coming 1.35. So now for our calculation, we will be selecting these numbers. Okay. So these are the numbers, that's what we are selecting with. Now once we are selected with these numbers, what we know what is our radius ratio. So the radius ratio at the entry, this station radius ratio, that's what is given to us. So that's what we will be putting, say 0.375 into this radius what we have calculated, it is 0.258. That's what is giving me my hub radius at the entry and my tip radius at the entry. Okay. So now we can say, based on our understanding, we are finalizing our entry dimensions at the tip, we are finalizing our entry dimension at the hub, and this is what we are doing calculation at the say entry. Now here we are stopping with. In next lecture we will be discussing how do we do our calculation for station 2 as well as for station 3. I am sure this is what is giving you idea what all can be done in sense of starting with the initial design part at the entry. Maybe as we have discussed, you can go with some other approach and you can come up with these numbers. Okay, maybe you can assume your Ca by U value, you can assume your degree of reaction, you can assume your tip diameter, and that's how we will be doing our calculation. So here we are stopping with. Thank you very much for your kind attention. We will be continuing our design in the next lecture. Thank you.